Hi, my name is Laura Zager, and today we're going to be exploring an incredibly beautiful and fascinating area of mathematics using algebra and complex numbers. Let's get started with an experiment called the chaos game. On the board behind me, I have an equilateral triangle with its three vertices labeled red and blue and green. And here on the table, I have a six-sided die with two faces colored red, two faces colored green, and two faces colored blue. Here's how you play the game. Start by picking one of the three vertices. I'm going to pick the blue one, but you can pick any one you'd like. And draw a dot at the vertex that you've chosen. This is going to be your starting point. Next, roll your die and observe which color comes up. So I've just rolled a green. So what I'll do is I'll start with my blue point that I've just chosen. I'll look at the green corner, and I'll draw a new dot on the triangle halfway between my current point and the green corner. So if I measure roughly halfway, maybe I'll be here, and I draw a new point on my triangle. Now this is my new current point, and I'm going to repeat this procedure again. I'm going to roll the die, and I've gotten a red face. So I'll draw a new point on my triangle, halfway between my current point and the red corner. So, about here. I keep repeating this procedure, drawing lots and lots of dots, rolling the die, drawing a new dot halfway between my current point and the vertex corresponding to the color of the die. Now here's a question for you. If I keep doing this over and over and over again, drawing more and more dots, what do you think the pattern of dots in the triangle is going to look like? Or will there be no pattern at all? Do some brainstorming, collect your guesses, and we'll come back to this at the end of the lesson. Now let's change direction a little bit. Have you ever heard of the Fibonacci numbers? The Fibonacci numbers are a sequence of numbers defined by a simple rule. The first Fibonacci number, x0, is just defined to be 0. The second Fibonacci number, x1, is defined to be 1. The rest of the Fibonacci numbers are defined to be the sum of the previous two Fibonacci numbers. So x2 will be the sum x1 plus x0, which is 1 plus 0, just 1. x3 will be the sum x2 plus x1. x2 plus x1 gives us 2, and so on. And we can compute any number, x3, x4, x5. The Fibonacci numbers have interested mathematicians for over 1,000 years, both because of their interesting mathematical properties and also because of their tendency to arise in all sorts of natural patterns, like the golden spirals found in nautilus shells and in the shape of galaxies. Let's come up with a more mathematical way of writing down the Fibonacci number rule. If we want to find the nth Fibonacci number, xn, well, first we have to take into consideration our two special cases. When n equals 0, we know that the x0 Fibonacci number is just 0. When n equals 1, we know that x1 is equal to 1. But for every other value of n greater than 1, the nth Fibonacci number is just the sum of the previous two. The nth term will be the sum of the n minus 1th term and the n minus 2th term. We have special names for the relationships that are in this equation here. This relationship is called a difference equation. A difference equation is simply a rule that tells us how to get future items in the sequence from the items that we've already computed. These two relationships in our definition have a special name as well, and they're called initial conditions. Initial conditions tell us how to get started applying our difference equation. For the rest of this lesson today, we're going to be looking at difference equations that only require one initial condition. That initial condition we'll always call x0. If we also have a difference equation, then we can use the difference equation, apply it to x0 to compute x1, apply the difference equation to x1 to compute x2, and so on, computing as many terms in the sequence as we'd like. If we have a set of terms that satisfy a difference equation and an initial condition, we call that sequence of terms a trajectory. So just like following the path of a ball across the sky is following its trajectory, looking at the sequence of values that a difference equation takes is also called a trajectory. Let's look at an example together. Consider this difference equation. Xn equals 2 times xn minus 1 plus 1. And what we'll do is come up with a few different initial conditions and see what different kinds of trajectories result. Let's try for our first initial condition, x0 equals 1. Well, if we use x0 equals 1 as our initial condition, 2 times 1 plus 1 gives us the next term in the sequence, which will be 3. 2 times 3 plus 1 gives us 7. 2 times 7 plus 1 gives us 15, and so on. And we could keep computing terms in this trajectory if we'd like. Let's try another initial condition. Let's try x0 equals 0. Well, 2 times 0 plus 1 gives us 1. 2 times 1 plus 1 gives us 3. 2 times 3 plus 1 gives us 7, and so on. Well, what about another initial condition? Let's try minus 1. Well, 2 times minus 1 is minus 2. If we add 1 to that, we get minus 1 back out again. Well, if we apply the difference equation again, 2 times minus 1 plus 1 also gives us minus 1, and so on. So this trajectory will always stay the same. If we start with minus 1, we'll always get minus 1 out as a result. Okay, let's try minus 2. 2 times minus 2 is minus 4, plus 1 gives us minus 3. 2 times minus 3 is minus 6, plus 1 gives us minus 5. And 2 times minus 5 plus 1 gives us minus 9, and so on. So are there any patterns in these trajectories at all? Well, just from these experiments, it looks like when our initial condition is greater than minus 1, then the trajectories tend to get more and more positive. So if we continued computing the elements in this trajectory, they would just keep getting bigger and bigger. Similarly, when our initial condition was less than minus 1, it looks like the trajectory became more and more negative the further we went. But when our initial condition was exactly minus 1, the trajectory always stayed the same. It always stayed at minus 1. Here are a few more difference equations for you to try with your class. Choose some initial conditions, compute a few trajectories, and see what kinds of interesting patterns you can discover. Collect all of your answers, and we'll come back together. In the examples that you just explored, you saw that some trajectories tended to head off to infinity, either positive or negative, and some trajectories tended to stay finite. What do we mean when we say that a trajectory heads toward infinity? What we mean is that its absolute value tends to grow without limits or bounds. Let's try to come up with a mathematical way of saying this. We'll call a trajectory bounded if we can find a single number b such that the absolute value of every point in that trajectory is always less than b. Even if the b that we find is a really big number, like 10 million, if every point in our trajectory is always less than 10 million, we call that trajectory a bounded trajectory. If a trajectory isn't bounded, then it's unbounded. What does that mean? Well, it means that we can't find any such single number b such that every point in the trajectory has absolute value always less than b. Another way of saying this is that for any value b we choose, you can always find some point in the trajectory whose absolute value is greater than that number. Let's look at the example that we explored earlier. The difference equation, xn equals 2xn minus 1 plus 1. Which of the trajectories that we computed earlier is bounded and which is unbounded? Well, this first trajectory seemed to be continuing to grow. And in fact, every time we find a new term, it's going to be a little more than twice as big as the term before. That means this trajectory heads toward positive infinity, and this is in fact unbounded. The same is true for the second trajectory. These terms will continue to grow toward positive infinity. What about this last trajectory? Well, these terms are getting more and more and more negative, but their absolute values are getting bigger and bigger, and they'll continue to get bigger and bigger. This is also an unbounded trajectory. In fact, the only bounded trajectory of this difference equation is this one, where we start with the initial condition -1 and get -1 for the entire trajectory. To practice with the definitions of bounded and unbounded a little bit more, go back to the examples that you just worked in your class and decide which of the trajectories that you computed are bounded and which are unbounded. Now that you're all trajectory experts, let's consider a new difference equation. xn equals xn minus 1 squared plus c, where c is a constant that we haven't specified yet. This time, though, we're going to add a twist. We're going to let c be a complex number, not just the real numbers that we've been considering so far. Remember that a complex number has both a real part and an imaginary part. So in order to work with difference equations that are complex, we're going to need to know how to multiply and add complex numbers. When we're looking at this difference equation, let's assume that our initial condition is always x0 equals 0. We'll be interested in the different trajectories that result for different choices of complex c. Let's consider one example together. If we choose c equals 0, well, if x0 equals 0, our difference equation is simply xn equals xn minus 1 squared, and the result there is 0. And 0 squared is still 0, and will continue to be 0. So in fact, this entire trajectory is all zeros, and this is indeed a bounded trajectory. Now, as a class, consider these two possible trajectories. The choice when c equals 1 and when c equals I, where I is the imaginary number. Now, in order to decide whether these trajectories will be bounded or unbounded, you're going to need to be able to take the absolute value of a complex number. But that you already know how to do. So with your classes, decide if these trajectories are bounded or unbounded. Then we'll come back together and move on to something exciting. I hope you found that when c equals 1, the trajectory was unbounded. And when c equals I, the trajectory was bounded. Now here's an idea. What if we use the boundedness or unboundedness of these trajectories as a way of coloring in the entire complex plane? Here's what I mean. Here I've drawn the complex plane, the real axis and the imaginary axis. Here's our coloring scheme. For any point C in the complex plane, we'll color that point C red if the difference equation xn equals xn minus 1 squared plus c is bounded when our initial condition is x0 equals 0. And we'll color that point green if xn equals xn minus 1 squared plus c is unbounded with the initial condition x0 equals 0. So for example, we've already computed a few of these. Let's fill them in. We found that when c equals 0 and c equals I, these trajectories were bounded. That means we'll color these points in red. Here's c equals 0, and here is c equals I. c equals 1 corresponded to an unbounded trajectory. So we'll have to color in c equals 1 green. What we'll do next is take all of the red points and combine them into a set we'll call M, which stands for the Mandelbrot set. The Mandelbrot set is named after Benoit Mandelbrot, one of the first mathematicians to be interested in this set. Now here's my question for you. If we were to consider every single point in the complex plane and color it either red or green according to whether or not its resulting trajectory was bounded or unbounded, what do you think the pattern of points would look like? Or would there be any pattern at all? Take some time to brainstorm about this with your class. Then we'll come back together with a really surprising answer. In fact, the Mandelbrot set looks like this. What a surprising and complicated shape. Let's zoom in on the boundary of this shape, just to see what happens. You'll notice that as we zoom, the piece that we see looks just as complicated as the original shape. Indeed, we'll also see repetitions of the original shape, of the larger outline, appearing the more that we zoom. This property is called self-similarity. In fact, no matter how far we zoom, the boundary of the Mandelbrot set will always be just as complicated and will never simplify. Because of this, we say that the boundary of the Mandelbrot set is a fractal. The word fractal was coined by Benoit Mandelbrot in 1975 when he noticed his computer producing some very interesting images according to the difference equation that we just studied. One of the things that makes the study of fractals so fascinating is that they appear regularly in nature, like in this cauliflower and in this cactus. Artists also love to work with fractals, using their computers to create incredible images based on difference equations. One of the most famous fractals is also the simplest. It's called the Sierpinski triangle. Here's how you build a Sierpinski triangle. First, start with a black equilateral triangle and remove an upside-down triangle from the middle, leaving 3 black triangles. Now, remove an upside-down triangle from the 3 remaining black triangles, and continue doing this for every remaining black triangle. And continue this whole process an infinite number of times. This set is a fractal because of its self-similarity. No matter how we zoom in on it, we'll always see the same thing. But removing smaller triangles from larger ones isn't the only way to generate the Sierpinski triangle. You remember the chaos game that we played at the beginning of this lesson? Well, I've written a little computer program to play it for us fast. Well, let's see what happens. Yes, it's the Sierpinski triangle. The relationship between the Sierpinski triangle and the chaos game is an incredibly deep and interesting one that I hope you're interested in pursuing after this lesson is over. I hope you've enjoyed learning a little bit about fractals today. Thank you so much for your time and for your energy. Hi there. I hope you're looking forward to this lesson. It's really been a joy to teach in my classroom, and I hope it's a joy to teach in yours as well. I have lots of things that I want to tell you, so please pardon my notes as we go along. So this lesson on fractals was designed for students who have a mastery of basic algebra skills. So in the United States, that often means maybe a 10th grade or 11th grade level, and that's the level that I've taught it at in the past. It also requires a knowledge of complex arithmetic, which is not a topic that gets taught in all of the algebra classes. So to achieve that topic and to prepare the students for the lesson, we've actually written a tutorial on complex arithmetic. Now, this tutorial can be used in a number of ways if your curriculum doesn't cover complex numbers. One way to do it is to assign it to your students as homework the night before you're to do the lesson. It's designed to start from the basics, from a student who knows algebra but knows nothing about complex numbers, and bring them up to the level where they can add, subtract, multiply, and take the absolute value of complex numbers. So it walks them through these steps, and it gives them some practice with it. Alternately, you could decide to actually work through the tutorial in your classroom. So take the day or a few days before you decide to do the fractals lesson, and give your students time in a group and with you to get comfortable with the mechanics of complex arithmetic before you launch into this material. We've also included in the written material that goes along with this lecture a very quick quiz on complex arithmetic. And depending on your class, maybe you'd want to use it the morning that you do this lecture or assign it in advance, just to check the comprehension of the students before you, again, launch into the more complicated material. So that being said, the actual mechanics of the math that's in this lesson are not too hard. They're addition, subtraction, multiplication of numbers. What's difficult about the lesson is that it introduces some really sophisticated new concepts for students that require kind of a lot of mathematical maturity. Difference equations, initial conditions, trajectories, boundedness. These are all really quite sophisticated ideas. So you're going to play a really important role in helping your students understand and feel comfortable and develop intuition about these new topics. So I hope you're up for the challenge. Okay, so let's get started. So part one of the lecture is an experiment called the chaos game. Now, in the video, I present it and suggest to the students that they pursue it as a thought experiment. So the way I've done it in my classroom in the past is broken the students up into pairs and had them work together and just brainstorm what they think the final pattern of dots is going to look like. Often it helps to hand each pair of students a piece of paper with an equilateral triangle already drawn on it, and that way they can kind of plot out some points and look at it and do some discussing. Alternately, you might want to try actually running this experiment in your classroom. And Robert Devaney is an educator who suggested one way to do this is to hand small groups of students or individual students an overhead transparency sheet, so a clear sheet of paper. You also hand them a permanent marker and then some kind of die or way for them to run the experiment. So some way of selecting red, green, and blue, or 3 equally likely things. So if you had a die, you could use a die. You could make your own, like the one I used in the video. If you wanted to, you could draw 3 different colored marbles out of a bag or out of a hat. Any of these ways would work just fine. So if you hand each of your students this overhead transparency sheet with a triangle drawn on it, and have them actually run this experiment and draw dots on the overhead sheet. Robert Devaney suggests that when you're finished with this process, you can take all of the transparency sheets and stack them up and then project through them onto the wall. And the idea is that this is a very quick way of generating a whole lot of points. And you should be able to get a sense of what the final pattern looks like. I think in order to make this successful, you'd have to have some really, really precise students. Because when I tried this with a group of teachers in the past, the result was a completely incoherent mess. We couldn't see any patterns at all. So I recommend doing some experimenting with this before you get started, before you bring it into your classroom. An alternate way of doing it would be to actually write a computer program that would do it. And actually, at the end of this lesson, in the very final section, we present the results of a computer simulation that's playing this game. If you have students in your class who are taking a computer programming class or who know something about computer science, this might be a fun project for them to do. Have them write a little piece of software that will do this, play this game for the whole class. It could be a really interesting extension. Okay. Speaking of extensions, you may get questions on extensions. So, for example, what happens if you don't start the game at one of the vertices, but you start at some point in the middle of the triangle? Are you still going to get the same kinds of patterns? These questions are what makes it a lot of fun to be a teacher. So the more thinking you can do about the kinds of questions your class is likely to ask and the answers to them, or at least giving them pointers to where they can explore the answers to their questions themselves, that could be really great. And the written material that accompanies this video lecture includes a lot of possible extensions. And so I hope you'll take a look through those and maybe get some of your more excited students to pursue some of those topics. Okay, so that's part one, playing the chaos game. Part two is the introduction to difference equations. Now, right away, some of your students may have trouble with this because a difference equation is very different than the kinds of equations they're probably used to seeing. In a lot of ways, it's more like a rule than kind of a formal equation that they're going to have to solve. We start to try to develop students' kind of comfortability with this idea of difference equations by talking about the Fibonacci sequence. Often in my classroom, there's been 1 or 2 students who have seen it somewhere else in their previous math background, but many students haven't. It's a really great topic, just the Fibonacci numbers themselves, for high school algebra and geometry classes because there's a very strong geometric component to the Fibonacci numbers. They have a lot of interesting applications, and there's a lot of interesting and not too complicated mathematics that can really give high school students a glimpse into what mathematics at the college level might be like without bogging them down in too much material that they don't have the background for. So I highly recommend encouraging your students to pursue different areas of applications of the Fibonacci numbers. And again, there are some discussions of that material in the written material that accompanies this lecture. So as I said, this section introduces difference equations and initial conditions. Really, what's needed more than anything here is just time and practice. Students need to get familiar with looking at a difference equation, being comfortable computing a trajectory, and experimenting with what happens with different initial conditions. A really useful format that you can apply to the problem solving that happens throughout this entire lecture is to break the students into small groups, present them with the examples that we discuss or that we present in the video, have them work in these small groups for a little while, and then bring the entire class back together and assemble all of their results so that everybody can see them. So if you can put them all up on the board, that's a really useful thing. And that's especially useful when you're talking about difference equations and calculating example trajectories, because then you can get a lot of different kinds of trajectories without having every student have to go through all of the different possibilities. Okay, so part 3, we introduce the idea of boundedness. And I think this is one of the more sophisticated ideas that gets introduced in this lecture. And I think you'll probably end up spending a lot of time helping students develop intuition on the idea of boundedness. So often I find it helpful to phrase kind of boundedness in the following way. If a trajectory is unbounded, then it's not possible to find any single number such that the absolute value of the trajectory is always less than that number. So if you can find such a number, even if it's a really big number, even if it's 100 million, if you can find a number such that the absolute value of the trajectory is always less than that number, then it's bounded. And you'll come up with all sorts of different ways of explaining what a bounded trajectory is versus an unbounded trajectory. A useful tool to use in the classroom is to encourage your students to challenge each other. So present a difference equation and an initial condition. Look at what the trajectory, calculate a few points of it, and then ask the class, is this bounded or unbounded? Often they'll have an intuitive answer. Well, it looks like it's blowing up or it looks like it's not. But see if you can get them to use the mathematical language. Ask them to prove it to you. Find me, if you argue that it's bounded, find me a number that the absolute value is always smaller than. If you argue that it's unbounded, tell me why. Another issue that often confuses students is when a trajectory is bounded, a number that serves as a bound for that trajectory is not unique. So, for example, if the absolute value of a trajectory is always less than 2, well, then the absolute value is always less than 3 as well. So students often find it difficult to kind of handle this non-uniqueness in terms of boundedness. So that's something you may have to discuss explicitly in your class. Okay. In part 4, we add a twist to the material we've done so far. We allow our difference equations to take on complex values. So maybe we give them complex initial conditions, or the difference equations themselves have a complex number in them. None of the mechanics are any different, but it requires them to use complex arithmetic. And depending on how comfortable your students are with complex arithmetic, this can be more or less difficult. This is another one of those topics that will just require time and practice. So having extra examples and allowing enough time for students to work through those examples can be really important to helping them feel comfortable with the idea of complex trajectories. Now, in order to evaluate whether or not a complex trajectory is bounded, students need to be able to take the absolute value of a complex number. And this is a topic that is addressed in the tutorial, but if you discuss complex arithmetic in your class outside of the tutorial, make sure that students know how to find the absolute value of a complex number in order for them to be able to work through this section. So part 5 introduces the Mandelbrot set. And in some ways, this is conceptually the most lovely part of this entire lecture. At this point, students need to feel comfortable with deciding whether or not a trajectory, a complex one, is bounded or unbounded, because that's the way that you define what points are in the Mandelbrot set or not. But hopefully, by this point, all of the hard work and heavy lifting has been done by your students in terms of the mechanics and kind of intuition building on trajectories. And they can kind of just enjoy the beautiful results that come out. So at the end of this section, we ask the students to guess what the Mandelbrot set is going to look like. And this is one of those times where you don't need to spend too much time in class on having students brainstorm and then coming back together with their suggestions, because the answer is so strange and seemingly unpredictable that it's really more a thought exercise at this point, and they're kind of waiting to see what the final answer is going to be. So the very last section is on fractals in general. And it really is just a very brief introduction to some beautiful images that will hopefully inspire your students to pursue some of the extensions that we were talking about earlier and to do future work in this field. At the very end, we also return to the chaos game and the Sierpinski triangle. And as I mentioned earlier, we present the brief computer simulation that shows you kind of the very surprising and interesting pattern that the chaos game will result in. And so I hope by the end of this lesson, your class has learned an extraordinary amount of new material, most material that students in high school never get a chance to see, and that all of you have kind of become interested in a brand new topic that could take you in all sorts of directions in algebra and geometry and beyond. So thank you very much for your interest in this lesson. I really hope you enjoy making this lesson on fractals exciting and interesting to your class, and I wish you the best of luck.